Hi, so welcome back. We had done 4 tests in the previous couple of videos. What I'm going to do now is run through, over a sequence of a couple of videos, the rest of the different types of tests for series. It may not be exactly in the same order the textbook does it, but by the time I get done with these couple of videos, we'll have covered what's in the rest of Chapter 10, which is a whole bunch of different tests that can be used to figure out whether a sequence or series diverges or converges. We'll start with the ratio test. The ratio test is one of these tests that can be used very often, but is not always our first choice to go to because it's a little bit more complicated. However, there are times when the ratio test is the only one that works. So suppose I have a series of positive terms. So if the sum of all the a sub n's is a series of positive terms, then what I'm going to do is I'm going to look at two terms that are sequential, and I'm going to look at how the limit behaves as n approaches infinity. So I'm going to take a term, it's called the n plus first term, and I'm going to divide it by the term before it. So if I had a series of a half, a quarter, an eighth, a 16th, I might take a 16th and divide it by an eighth, or I might take an eighth and divide it by a quarter divided by a half, to see what I get, right? That's going to be some value. I've got 3 options for the ratio test. If that value is less than 1, then the series converges. All right, so in other words, look at it in the other direction. If I'm always multiplying by a half, then I've basically got a geometric series with a ratio of 1/2. It's going to get smaller. If that value is bigger than 1, then essentially what I'm doing is multiplying by something bigger than 1 every time. Well, if I do that, that thing is not adding up to a finite value. That series diverges. There is a point at which the ratio test fails me, and that is if the two terms are too similar to each other, then I take their limit and that limit approaches 1, and so we say the test is inconclusive, which is nothing to worry about because we have like 9 of these tests by the time we get done. And so if 1 doesn't work, you got 8 more. Not a problem. All right, let's take a look at a couple of different cases where we can use the ratio test and some cases where the ratio test might be our only choice. So let's look at the sum from k equals 1 to infinity of 2 to the k over k factorial. Well, what else could we use supposing we didn't want to use the ratio test for this? We can't use the nth term test because I bet you k factorial grows faster than the exponential function, so that'll go to 0. That's not what we want for the nth term test. It's clearly not a geometric series, so we can't use a geometric series test. Can we use an integral test? I don't know. Can you integrate a k factorial? Is not a p-series, so we can't use the p-series test. So for now, let's try using the ratio test. Now, the ratio test gets messy before it gets better. Here's what it looks like. I'm going to take the limit as n approaches infinity of the n plus first term. Well, the n plus first term replaces all those k's with k plus 1. So I get 2 to the k plus 1 over k plus 1 factorial. And now I'm going to divide it by 2 to the k over k factorial. Remember the old rule about invert and multiply? So I get 2 to the k plus 1 over k plus 1 factorial. Now multiplied by k factorial over 2 to the k. All right, let's separate this in a way that makes sense. So let's move this down a little bit. I'm going to end up with, let's put the 2 to the k plus 1 and 2 to the k together over here, and then I'm going to put a k factorial over k plus 1 factorial. Well, k plus 1 factorial, isn't that k plus 1 factorial the same thing as k times 1 times k times everything before it? If you see that trick and you get used to using it, it's going to come in handy many, many times, right? So if I can make that k plus 1 factorial, k plus 1 times k times everything before it, that simplifies life a little bit. All right, this first piece over here just becomes a 2, right? 2 to the k plus 1 over 2 to the k is just 2. The second piece here, the k factorials cancel, and I end up with 1 over k plus 1. When I slide this up once more and put my limit in there, I'm really looking at the limit as k approaches infinity of 2 over k plus 1, which is 0. This thing here is the L that I've been looking for. So if that thing is less than 1, then the series converges. Which I guess is not terribly shocking considering we know the k factorial is going to grow faster than the 2 to the k. The only question is it going to increase in the denominator fast enough that that whole thing converges, that those little pieces that I'm adding are small enough that the whole series converges. So here's a case where I didn't have much of a choice. I kind of had to use a ratio test, and so we did. All right. You'll notice ratio tests tend to appear when there are exponentials. So let's look at this series. Let's look at the sum from n equals 1 to infinity of 2 to the n over n to the n. So I might do the limit as n approaches infinity. After a while, you're going to stop writing those massive fractions, and you're going to write things like this, 2 to the n plus 1 over n plus 1 to the n plus 1, right? Remember, if you're bumping this up by 1, all of those variables also go up. And then I'm going to multiply by the reciprocal of the original functions. The reciprocal of the original one is n to the n over 2 to the n. Now, as you do this, do it in a way that makes sense, right? These things are being multiplied, so you can move them around as long as you keep numerators and denominators separate. So I got a 2 to the n plus 1 on the top. I got a 2 to the n on the bottom. What do I have in the other piece? The other piece has an n to the n, and, well, that n plus 1 to the n plus 1, what if I rewrote that as n plus 1 to the first times n plus 1 to the n, right? So I'm taking this thing over here, and I'm saying n plus 1 to the n plus 1 is a lot of n plus 1s multiplied together. How many of them? N plus 1 of them. So why not make n of them over here, and then I've got that extra one over there. Great. So how does that help? Well, that first piece just becomes a 2. So I'm left with the limit as n approaches infinity of that thing over there is just a 2, right? I've got one more 2 on the top than I do on the bottom. I've still got that 1 over n plus 1, but look what happens to the last piece. The last piece I can write as n over n plus 1 to the n, right? So I'm going to take those two exponents that are on the outside and pull them on the outside of a set of parentheses. Well, this gives me 2 over n plus 1 times n over n plus 1 to the n. It turns out that that second piece is actually something kind of special. All right, so this second piece here is somewhat special. If you remember what the definition of E is, the definition of E is the limit as n approaches infinity of 1 plus 1 over n to the n, right? That's how we define E. Well, if I combine these together, isn't this the same thing as n plus 1 over n to the n, which is exactly the opposite of what I have over here? It turns out this thing is really just 1 over e. If I apply that limit as n approaches infinity, that'll give me a 1 over e. If I apply the limit as n approaches infinity here, I just get 2 over a very large number, which is 0. 0 times a constant is just 0. It converges, right? Because the limit is less than 1. So start getting used to writing out why these things work. So in this case, this converges by the ratio test because the limit is less than 1. Right? That little trick you might not have seen on your own, but now that you've seen it once, now you might recognize that in future cases. So if you know what the definition of E is, and you can combine those terms over a common denominator, flip that common denominator, and now you've got another expression for the reciprocal of E, and look, it just happened to show up in a nice place and help us to solve the problem. All right, so that is the ratio test. The ratio test will appear many more times before you take the final exam, so we'll move on and look at a couple of other tests, and eventually I'm sure we'll hit some problems where you have to do the ratio test. All right, here's an easy one, the root test. Hey, root test is kind of like a p-series test, kind of like a geometric series test. It works great, but only in certain cases. So let's take a look at a series of the sum of all the a sub k's. And I'm going to let rho, right, that's the Greek letter rho, be the limit as k approaches infinity of the kth root of a sub k. So this root test applies oftentimes to cases where we have some piece on the inside raised to a power. And when we take the kth root of that, then we end up with just the piece on the inside, and we evaluate it, and it becomes very much like a geometric series test. So root test has 3 parts. If that limit, right, the limit as k approaches infinity, is between 0 and 1, then the series converges, right? Very much like a geometric series. If that limit is greater than 1, it diverges, and if that limit is equal to 1, then that test is inconclusive. All right, meaning that I don't have enough information to know whether those pieces that I'm adding are small enough for the series to converge, or if it's going to cause a problem, the series will end up diverging. So I'll do one example. I think that this thing you'll catch on pretty quick. Suppose I have this series. The sum from k equals 1 to infinity of 4k squared plus k over 9k squared plus 1, the whole thing raised to the kth power. So this here is my a sub k. For the root test, I want to take the kth root of a sub k. So when I take the kth root of a sub k, you realize that I just get what's on the inside there. So I'm going to let rho be the limit as k approaches infinity of 4k squared plus k over 9k squared plus 1. So you can L'Hopital this a couple of times. You could even divide top and bottom by the highest power. You realize that as you take that limit as k goes to infinity, you'll end up with 4/9. All right? So where does 4/9 fit in there? 4/9 is between 0 and 1. So because that 4/9 is between 0 and 1, therefore this thing converges. Right? Because essentially what it's saying is that you have a geometric series and you're multiplying each term by 4/9. Well, if you keep multiplying each term by 4/9, then eventually that thing is going to converge, right? The terms are going to get small enough that it'll approach some constant. All right, so that was the root test. Let's take a look at the first of our comparison tests. It turns out that, yes, there is more than one comparison test. This one, we're going to do the direct comparison test, and then we'll do another video with some of the other tests. So let's look at the direct comparison test. All right, so the idea is this. If I don't know what a series does, and it's a very complicated series, can I instead compare this to an easier series that hopefully it's easy enough I can do in my head, and then whatever the one series does, the other series will do too. So I'm going to have 2 series, right? Sum of all the a sub n's, sum of all the b sub n's. They're going to be series of non-negative terms such that the b sub n terms are always greater than or equal to the a sub n terms, right? So one series has terms that are all bigger than the other series. All right, let's think about what this means in terms of a graph. Right? Suppose you have 2 functions. All right, so I'll come back to the definition in a second, but suppose I've got 2 functions, right? And I'm going to use a's and b's. I've got this bigger function b that converges. All right, so this function b converges, meaning that the area under the curve there is finite. So suppose comes along this function a that's always smaller. Well, what can you tell me about the area under the curve here? Well, if the bigger one converges, then the smaller one has to converge also, right? There's no way that this bigger one converges and has a finite area, but yet the smaller one has an infinite area. That's not possible. Okay. Suppose I flip this around for a second. Suppose I have, again, b sub n is the bigger function, but now suppose that b sub n diverges. Well, if that b sub n diverges, then what can I say about the a sub n? Nothing, right? Because that a sub n, I don't know. It could be enough that it converges, or it could also be infinite. All right, let's look at the other cases. So this is a case where the a sub n then also converges. The third case then would be, what if I know that the a sub n diverges, right? So here's my b sub n. Here's the a sub n. If I know that this thing diverges, well, if that area is infinite, then there's no way that the top one can be finite. The top one also has to diverge. Okay. The fourth case doesn't give us any information. So what if I knew that the smaller one converged? That doesn't tell me anything about the bigger one, right? The bigger one could diverge or it could converge. So if you think about it graphically, that might help you out to figure out which one is which. This will have two cases that work and two cases that don't work. So how can we write this out? If the bigger one, so if the B sub n converges, then the A sub n converges also, right? You might think of it simply in terms of if the bigger one converges, the smaller one has to converge, right? So if the bigger one has a finite area, the smaller one has to have a finite area also. And then the second part of this test is actually the one that's illustrated right here. If the smaller one diverges, then the larger one diverges also. And I'm going to say here that the other two cases are inconclusive. Not to worry, there's another test coming for those. All right, so if the bigger one converges and the smaller one converges, if the smaller one diverges and the bigger one diverges, the two cases in between, we can't tell. We're going to need a different test for. All right, so these comparison tests are going to involve two parts. You can't do a comparison test just with one piece. These comparison tests mean that you're going to have to perform two tests. So, for example, suppose I want to find the sum from n equals 1 to infinity of 1 over 2 plus 3 to the n. And of course, my question, as it's been all day, has been, does this converge or diverge? Well, I don't know. It doesn't seem fun to try to perform integral tests with this. And if I can avoid having to do the ratio test, I'll try to avoid having to do the ratio test. So maybe I can do a comparison test. How do you decide what to compare it to? Well, you compare it to a much simpler formula that's easy to use. So I'm going to compare it to this. Why? Because I can write it like that, and suddenly it becomes a geometric series. So the first question is this a useful comparison? Well, in a couple of cases, you kind of almost have to know where you're going with this. This thing over here is a convergent geometric series. So this thing here is a geometric series with a ratio less than 1 that converges. The question is, how does it compare to the original series? Well, how does 1 over 2 plus 3 to the n compare to 1 over 3 to the n? Well, as I add terms to the bottom of this, then that one's going to get smaller. So it looks like the comparison works that way. That 1 over 3 to the n will always be bigger than my original series. So if the larger one converges, right, the larger one converges, therefore the smaller series must also converge. Okay, so what can we conclude? We can conclude that the original series, the 1 over 2 plus 3 to the n, converges by the direct comparison test. I'm going to be cheap and call it the direct comparison test like that, and a geometric series test. You'll never have a series converge or diverge just by the direct comparison test. It's got to be the direct comparison test and something else. Or eventually we'll do a limit comparison test, and you can use that, but it's got to be done with something else. Because once you determine that it's a good thing to compare it to, well, then you've got to actually perform the test to see whether it converges or diverges. All right, let's try another one. Let's take a look at the sum from n equals 2 to infinity of 1 over the square root of n squared minus 1. Right? Now you know I didn't start that at 1. I started at 2 instead to make sure that all the terms are defined. If I try to look at this and say, what am I going to do? I mean, I suppose I could integrate. I'm going to end up with inverse trig functions, but yeah. To avoid that, maybe I can do a comparison test. So what should I compare this to? Well, what's the most important part of the problem? It's got to be the 1 on the top and the square root of n squared on the bottom, which is just 1 over n. So I'm going to use this series 1 over n as my comparison. So this will be the sum from n equals 2 to infinity of 1 over n. We've done about 4 of these already. You can pick which test you like. You can call it a p-series with p equals 1, and therefore it diverges. Right? You could even get away with just saying that it's simply the harmonic series, and the harmonic series diverges. So that thing diverges. Now, the question is, how does that series compare to the original? How does 1 over the square root of n squared minus 1 compare to 1 over n? Well, as I subtract values here, it's going to make the denominator smaller. Smaller denominator means larger function, therefore it works out that way. Well, if the smaller one diverges, right, if the smaller one diverges, then the larger one has to diverge also. Okay, so that's a case where the direct comparison test works great. If the smaller one diverges, the larger one diverges. So my conclusion is that the original series diverges by the direct comparison test and a p-series. Right, so I'm going to not only say that it converges or diverges, but I'll also state the test. Right, you could see that we had done a problem before that involved the 1 over n squared plus 1. Right? We had a series problem like this that we did using the integral test. Right? We had done this and we had come up with an inverse tangent using the integral test. Is it possible we could do this with a direct comparison test? How does 1 over n squared plus 1 compare to 1 over n squared? Well, again, as I add more values on the bottom here, that makes them smaller. So if this is the smaller one and that's the larger one, it actually works out like this. Well, the sum of all the 1 over n squares is a convergent p-series. So I could have said before, use the p-series, and if the larger one converges, the one underneath it converges also. So we had done it before using an inverse tangent and an integral test. We could have also done it this way had we known that like 20 minutes ago. So this thing converges by the direct comparison test and a p-series, right? P-series with p greater than 1, it converges. All right, so that's the end of this part. I will break this apart into a second video. We will do some more comparison tests and other types of tests to see whether or not series converge.